Imagine you're holding two of the most advanced cosmic rulers humanity has ever built. One is the legendary Hubble Space Telescope, orbiting Earth since 1990. The other is the James Webb Space Telescope, our newest eye on the universe. You'd think, with tools this powerful, we'd finally agree on how fast the universe is expanding. But strangely, we don't. This disagreement isn't just a tiny rounding error. The numbers diverge so much that cosmologists are calling it the Hubble tension. And the answer, whichever side turns out to be right, might force us to rethink the very foundations of cosmology. So what's going on? Why are these two scientific giants, Hubble and Webb, giving us conflicting numbers about something as fundamental as how fast the cosmos is stretching apart? Think about it like this. You and your friend both have a measuring tape. You measure the same living room wall, and your tape says 3 meters, but your friend's tape insists it's 3.5 meters. At first, you'd suspect someone's tape is broken. But what if both tapes are accurate, just calibrated differently? That's exactly the cosmic puzzle astronomers face today. And here's why you should care. This isn't about abstract numbers in textbooks. This is about whether the universe is stranger than we ever imagined, or whether we've misunderstood something fundamental about its birth and evolution. The constant that isn't constant. Let's start with the basics. The universe is expanding. We've known this since Edwin Hubble and Georges Lemaitre discovered it in the 1920s. The rate of that expansion is called the Hubble constant. It's measured in kilometers per second per megaparsec. In plain English, it tells us how many kilometers per second a galaxy is moving away for every million parsecs, or distance. Think of it as the speed limit of the cosmos. For decades, astronomers have worked to refine this number. And here's the twist. The closer we look, the more stubbornly the numbers refuse to line up. Hubble's measurement. The Hubble Space Telescope measures expansion by looking at standard candles. These are cosmic light bulbs whose brightness we understand well, like Cepheid variable stars or Type 1a supernovae. By comparing their intrinsic brightness to how dim they look from Earth, Hubble gives us their distance. Combine that with redshift, the stretching of light caused by expansion, and voila, a measure of how fast space is growing. Using this method, Hubble consistently finds a Hubble constant around 73 kilometers per second per megaparsec. Planck's counterpoint. But here comes the challenger. The European Space Agency's Planck satellite, which studied the afterglow of the Big Bang, the cosmic microwave background, arrives at a very different value, about 67 kilometers per second per megaparsec. This is not a trivial difference. It's like two weather forecasts disagreeing on whether tomorrow will be a gentle breeze or a full-blown storm. Both can't be true in the same universe. And now James Webb has entered the ring, with sharper eyes and more powerful instruments. Many hoped it would settle the fight once and for all. Instead, it made the debate even louder. James Webb steps in. Webb was designed to see fainter stars, farther galaxies, and with more precision than Hubble ever could. Its infrared vision cuts through dust and allows us to study Cepheids and distant supernovae with unprecedented clarity. So what did Webb find? Surprisingly, Webb's measurements of Cepheids confirmed Hubble's results. They weren't calibration errors. The 73 number holds, which means Hubble wasn't wrong after all. This, ironically, deepens the crisis, because if Webb and Hubble agree, then the discrepancy with Planck's early universe measurement becomes even harder to ignore. Two eras, two stories. Think of it like this. Hubble and Webb are reading the story of the local late-time universe, what's happening nearby billions of years after the Big Bang. Planck is telling us about the early universe, just 380,000 years after creation. If these two eras give us different answers, then either our understanding of the cosmos is incomplete, or there's some new physics bridging the gap. Dark energy, exotic neutrinos, modifications to gravity, all are on the table. It's as if history books and eyewitness accounts of the same event describe two completely different stories, both reliable, both internally consistent, but somehow mismatched. Why this matters. Now, some of you might wonder, why should I care if the number is 67 or 73? Does it change my daily life? Not directly, but it changes the story of the universe we live in. If the higher value is true, the universe is younger and expanding faster than we thought. If the lower value is correct, it's older and more sedate. Each scenario has profound implications for the role of dark energy, the fate of galaxies, and even the ultimate end of the cosmos. And beyond the technical side, there's something deeply human about this debate. It shows that even with our most powerful machines, the universe still holds secrets we haven't cracked. Possible explanations. So what are the possible answers? One option is that we're missing something in the local distance ladder, some bias in Cepheids or supernovae, but Webb's confirmation makes that less likely. Another is that Planck's early universe assumptions are incomplete. Maybe new particles, like sterile neutrinos, changed the physics of the early cosmos. Or maybe dark energy didn't behave the same way billions of years ago as it does today. There's also the radical possibility. Einstein's general relativity might need a tweak at cosmic scales. That would be a revolution on par with Copernicus saying Earth isn't the center of the universe. The road ahead. So what comes next? Projects like the Vera Rubin Observatory and the Nancy Grace Roman Telescope will add enormous new data sets, and gravitational wave astronomy might soon offer an independent way to measure cosmic expansion. If these new methods align with Hubble and Webb, the pressure on the standard model of cosmology will grow unbearable. If they side with Planck, it might mean our local measurements are being tricked by something subtle we haven't spotted. Either way, the resolution of the Hubble tension will likely reshape 21st century physics. It could lead us toward new laws of nature or confirm that our current framework is more resilient than we imagined. Closing. So next time you see one of those breathtaking James Webb images of distant galaxies, remember, under the beauty there's a fight going on. Two rulers, two answers, one universe. And until we find out why their numbers don't agree, the greatest mystery of cosmology is still wide open.